session into order. All right. So this is our parallel session on dust, atmosphere, and magnetism, and apparently true polar wander of the moon, which is totally related. Okay, so let's see. Our first talk is going to be William Yu, who's doing numerical modeling of dust dynamics around small asteroids. And go ahead.
All right, thank you everyone for coming in for my talk. My name is William Yu. I'm at the University of Southern California, my last year PhD program in astronautical engineering, and I am under the advisement of Dr. Zhao Wang, and I'll be talking to you about modeling dust grains around small asteroids. Thinking. All right. While we're waiting, really like to thank Dr. Rainey for giving the background science, saving me the trouble. All right. Okay. So as we all know from recent rendezvous missions, images have shown that even small asteroids have a layer of regolith on it. And lofting of dust grains have been suggested for the lunar environment, and similar behavior could be exacerbated on the asteroid environment. Of particular interest are small asteroids, where the tenuous gravity is no longer the dominating force on the dust grain and is instead actually having to compete with other effects such as local electric field, global magnetic field, solar radiation pressure, among others. So my talk will be focused primarily on dust grains that are electrostatically levitated and subsequently transported around the asteroid. All right, this may not be working here. Next slide. There we go. All right. So there are other groups that are looking into dust transport models with limitations, and specifically they tend to focus on a particular plasma charging environment, such as the full electron sheath layer or the plasma wake environment, and they predominantly, these simulations are limited to two-dimensionals, assuming a point source gravitational field for a spherical or near spherical asteroid. In addition, typically simulations do not solve the surface potential self-consistently, and typically assumes that the dynamics of the plasma interactions are with isolated dust grains. So in contrast, my work will be looking at the overall global environment of the asteroid in a three-dimensional simulation, without having to assume finite point source for my gravity field. And I'm also looking into the charging of a dusty surface as opposed to an isolated dust grain. So the overall goal is to look at the global environment around the asteroid, how that might influence the dust grains. So I have to take into consideration local plasma surface interactions, which would yield surface charging and that could lead to dust levitation, transport, and that could have implications on the evolution of the solar system as well as future spacecraft designs for further exploration. So to achieve this, I have a four-prong approach. First, I need to determine the electric field around the asteroid through a plasma asteroid interaction model. Dust surface charging is estimated by laboratory measurements, and gravity field is modeled using a finite element to realistically model asteroid surfaces, and that gets all fed into a dust transport model, which is governed by the equation on the bottom. So first, our plasma asteroid interaction model utilizes a fully kinetic immersed finite element particle in cell field solver, which considers solar wind ions and electrons and photoelectrons in a model with realistic ion-electron mass ratios. The surface of the asteroid is considered as an interface where the surface potential and the electric field around the asteroid can be solved self-consistently by charge deposition. So our laboratory measurements, we have a plasma source that simulates the solar wind conditions, average solar wind conditions, where we exposed the plasma to a dielectric surface. We've done measurements on a dusty surface with aluminum silicate and JSC1A as well. So we measure the surface potential as an input parameter for my models for the dust transport. And for the modeling the gravitational field is actually a difficult astrodynamical problem. The most straightforward approach is to use a model called the finite element mass concentration model, or FE-MASCON, and this model has been used to study the gravity around Itokawa, Cleopatra, and with fairly accurate results and with an overall accuracy within 1% error of the gravitational acceleration. Although that gets a little worse towards the surface, it's still within 10% error. And another feature of this model is that it is capable of varying the internal density of the asteroid for a more realistic model. So here we have my dust transport model with the governing equation on top, where we feed in the electric field information from my plasma asteroid simulation, the gravity field from my FE-MASCON model, and here we also implement forces from solar radiation pressure onto the dust. So before I get into the results, here are some of the quick parameters for my simulation. I'm considering a hypothetical asteroid that is spherical in size of 1 kilometer, and our dust grain are 20 microns with also spherical under average solar wind conditions at 1 AU. So these are near Earth asteroid conditions. Here's our simulation setup. The domain is 120 cells in the X, 30 in the Y, 30 in the Z, with solar wind ions and electrons drifting along in the X direction. And I make use of the axial symmetry, so this is only a model of a quarter sphere, and to limit the computation demands. So I have a few simulation cases to show. First with the baseline parameters, as I mentioned. So we'll see some density contours, surface potentials, and electric field and trajectory around the asteroid. Then I'll get into some comparisons with the case where I double the charge mass ratio, one where I ignore the photoelectrons, and finally the effect of a smaller dust grain and how those distributions would differ. So this is my results from my plasma asteroid interaction model. On the first one, you see density contours for solar wind ions where they're drifting in this direction and there's a clear wake formation. The electrons are much more mobile, so they're able to fill in that void, that wake void. We have the contour for those photoelectrons that are emitted on the day side, along with the contour of the potential field. If we take a little closer look at the potential field near the surface, we see that differential charging, which is consistent with what we see on the lunar surface and with theory. And those differential charging are also shown in the electric field vector on the right here, with the strongest electric field being along this terminator, the day-night region. Here is a sample trajectory for some dust grains that are electrostatic levitated and then transported. You see some dust remain near the surface, while others is capable of actually accelerating and leaving the gravitational well of the asteroid. Here is a simulation, if we could get that to play. So the dust grains here are being accelerated or being charged and electrostatically levitated. Some, as just like in the previous slide, some are staying near the surface, while others are leaving and escaping the trajectory or the asteroid's gravitational field. All right, so the resulting distribution looks like this for that model. And as you can see, the distributions for a spherical asteroid is aspherical around it. And there also so in the red region where there's a high density, would suggest that the electric field is able to transport dust grains towards the day side. And if we were to take some 1D profile with respect to altitude for the dust densities, we see that there are two distinct curve fits here within half asteroid radius. We see that there's a scaling that fits the exponential scaling, which may be analogous to what you might see for the neutral density in the atmosphere, whereas in higher altitudes, the dust densities conform towards a power law, one that here you see minus 2.8 for this line, minus 3.8. So it's getting towards minus 2 or a inverse square relation, which would suggest the gravity is now the dominating factor. So a little summary of what I already mentioned. The plasma-asteroid interaction is compatible with what we've seen from lunar observations and theory. Distribution is asymmetrical and tend to be mobilizing towards the day side. The low altitude at a low altitude, we expect a strong electric field influence. And at higher altitudes, gravitational fields seem to dominate as we see an inverse square relations for those dust profiles. So moving on, a few comparisons with other results. On the left is what I already showed, and on the right is the case where I double the charge to mass ratio. And what we see is it looks a little more symmetric, but more importantly, the dust grains are staying, are remaining around in orbit of the asteroid as opposed to actually ejecting. We still see a high concentration of densities moving towards the day side. Here I'm ignoring the photoelectrons on the right, and what we see is we don't see as many electrons or many dust grains moving to the day side, and we also see more dust grains that are leaving the surface. So without photoelectrons, we actually have a weaker electric field. So a weaker electric field seems to have a strong influence on the dust distribution. Looking at the same dust profile, you see the same curve fits, two regions, but the main takeaway here is with the weaker electric field, we're getting even closer towards that that inverse square relations. So further suggesting that with a weaker electric field, that gravitational field is a dominating factor, more dominating factor. And finally, here's a comparison for dust grains of 20 microns versus 20 nanometers. And what we see is with a smaller mass, the dust grains are more readily ejected from the surface. So you see fewer electrons on the surface and more leaving the surface. So the dust grain size is also another parameter to consider. The gravity can be also characterized. I haven't done that yet, but moving forward, I can easily implement a more complex asteroid model. And here's a summary of what I discussed. Dust distribution is asymmetrical and tends to be higher on the day side. Electric field dominate the low altitude, whereas gravity tends to dominate the high altitudes. These other charge to mass ratio, electric field, grain size are all considered parameters, and gravitational field will be something I will characterize further moving forward. With that, I'll open up to any questions.
Okay, thanks a lot. We have a few quick questions. We had a delay at the beginning.
So that's a really cool presentation. So if you didn't have spherical grains, if you just played the experiment, you'd expect that aspherical grains would be aligned when they were.
Yeah, I would expect there will be some some dipole going on where they would align with the electric field. So that's something I have to consider for a more sophisticated dust grain model.
Diane Wooden, NASA Ames, great talk. I don't have a great intuition for plasma processes. So when you double the charge to mass ratio, why does it cause there to be more of like an atmosphere compared to streaming away?
Essentially what's going on is when you double the charge mass ratio, you're effectively doubling the electric field force on the dust grains. So in essence, you could also get the same effect by doubling the electric field. So it's a result of the charge on the dust grain and the electric field.
Okay, awesome. Thanks, William. And next up is Cesare Grava.